Okay, question 3. This is something that you haven't dealt with before, but you learn about the triangular elements, and you know the broad elements, so on forth. Okay, anyways, let's work on this. So you have a row sign, okay, and the row sign is there's a 1,000 pound acting on top of the row sign. The the post is a 5 feet long, okay, and the plate is a quarter-inch thick, and each bar is 5 feet. Okay, 1,000 pound weight is placed on top of the sign as shown. Okay, apply the symmetric boundary condition and perform FE on the row sign. Number 1, determine the local stiffness matrix of the bar. Okay, let's call that A1. A E over L. So right here, A is a 10 inches square. E is a 6 degree. Length, remember, this is a right here is 10 inches square. Right here is 5 feet. Do not write 5, no. 5 times 12. Okay. 5 times 12 is 60. So 6e to the 3 divided by 6 will be 1e3. Easy. Now, let's pay attention here. Okay, on this exam, I already provided the D transpose times E matrix times D transpose. Okay. But in the final exam that you're going to work on next week, I will not provide that because for that exam in 2018, I try to help the students by already doing this Excel matrix form for them. But somehow it's not helping them. It kind of confused them. So this year, you determine the stiffness matrix based on the coordinates of the 2D elements, and then from that 3 coordinates and the dA and Poisson ratio, whatever you drive it, and you determine the stiffness matrix for the 2D elements for me. Okay, it will be a 6 by 6 matrix. Yes, you may use Excel in your final exam, and you just copy and paste that stiffness matrix into the into your writings. You have questions on this part? Do you? Any chat? You don't have to submit the Excel to me. You just you keep your Excel spreadsheet to your own. But I need that matrix. I need that 6 by 6 matrix. This is a 6 by 6 2D element matrix. Okay. Keep the Excel to yourself. Okay. I just need the results of it. Okay. Anyways, let's move on. So let's assume we have that 2D elements matrix already. Okay, and let's carry on. First step, we define the displacement vector. It's going to be, so again, I already defined the nodes for you already. See, the tip is nodes 1, nodes 2, nodes 3, nodes 4. Just move on with this nodes. Do not rename the nodes. Okay, you just make yourself make things complicated. Okay, the displacement vector for the 2D element is u1 v1 u2 v2 u3 v3, and then finally 4 is a u or v. Okay, it is a spring element, usually it's u, but because I place it in a vertical manner, right? So v, so 4 is a v4 as well. Now, the stiffness matrix for u1 to u1 to v3 is very straightforward. You just get this matrix. I should write it longer. You just get this matrix from Excel. Okay. Now, and then we add this 1e3 to where is 1e3 go to? v2 and v4, v2 v4. Okay. So 1e3 goes to right here, 1e to the v, and v2 is right here, negative 1e3. Somewhere along here will be 1e3, negative 1e3. Wow, what a mess. But you know what I mean? Okay, just from the put the address, put the destination note right beside the local matrix. Then it will guide you to place the stiffness matrix in the proper location. Okay, and the force vector right there. Okay, is a F1x, F1x, and F1y, F2x, F2y, F4y. Okay, now let's apply the boundary conditions. Okay, U1, I assume the whole thing is a religiously symmetric. Okay, so it's not swinging to the left or right. So U1 has to be 0. Okay, now it's kind of dangerous here because I'm not applying any force on x direction of node 1 as well. Technically, I can do that as well, but I don't want to have like 2 boundary conditions on both sides. So you know what? I leave it there. I leave it there for now and let the boundary condition on the right side to determine the F1x. I know for sure F1x will be 0, but based on the boundary condition on the right side. But it doesn't matter, you know, just keep this way for now. Okay, because when once you multiply, you know, everything just vanish. Okay, F1y. there is applied force to it. It's not 1,000. It's maybe 500. Okay, hang on. Someone just say something. Well, if you do not mind my messy writing, yeah, I can post it, and this being recorded and will be in YouTube. Okay. Okay, let's carry on. F2x. F2x. I have nothing there. I have no force acting on F2x. Do I have external force on F2y? No, nothing. Nothing at all. F3x. F3x. I know this is F3x. Again, same thing. I know F3x is 0, but I let a U3 to drive it because applying U3 to 0 is more helpful for me to solve the problem. F3y, I do not have any force acting on the y direction in 3, 0. F4y is some reaction force on top of it. Okay, now let's double check this side. U1, yes, it's 0. V1 is going to sink a bit. U2 is going to sink a bit because the whole thing with the 1,000 pounds is going to sink the notes 2 as well. U3, yeah, it's not moving anywhere. It's just symmetric. V3 will sink. V4 is locked in place. 0. Now, with this, you just multiply the displacement vector to the matrix, and you get four equations for a known. And with some manipulation, with some calculation, you get that V1, V2, V3, V3, V2. And when I say how much does the weight sink, we are looking for V1. V1 tells you how much does the weight sink. Any questions so far? Yep, I will post this notes to Avenue to Learn. Don't worry. Well, it's kind of messy, but okay. Why not? Okay, let's move on. Question 4 is a modal analysis question. Okay. Basically, I am not testing anything here. I'm just asking you to rewrite the note from the modal analysis course note. Use two beam elements of equal length determine the global matrix K and the consistent matrix, mass matrix. This thing is being published already. And the thing is, applied boundary condition do not solve for natural frequency. So what you did is pick up that note. Yeah, that's right. That's the note. So that's wrong. That's the one. Okay. 2 years ago, the final exam, question number 4, basically is an example 2 for modal analysis. The stiffness matrix is this one right here. And then the consistent mass matrix is right here. That 4 by 4 matrix. You add them together. Okay, you guess this. And then after you apply the boundary conditions, you just, when you write your note in the final exam, up to this point, up to this point right here, you just rewrite, you put this term right there, and minus omega square times identity matrix. You stop right here, then you find you get all your marks. Okay, and I didn't ask you to solve for this. Okay, you may carry on, but this is just an exact copy of the note. Any questions so far? Okay, let's move on. Question 5 is thermal analysis questions. Okay, does it look familiar to you? Where have you seen it? Hmm?
That's our quiz.
Exactly. Now, I might as well go through it. So okay. Okay, we have a watchtower. It's 40 feet, steel columns, uniform cross section, 50 pounds inch. It serves as double deck watchtower. The weight and the height of the deck is illustrated in the left figures. It's a hot summer day, so of course that column is gonna grow, but we have some weight on it, so it's being pressed as well. It wants to grow and it's being pressed as well, so it's a disaster for the analysis. So we just have to calculate the stress. Uh, oops, sorry guys, wait a second. Okay, now first step. I already posted the solution to the Avenue to Learn. First step, you define determine the global matrix. Okay? The local matrix will be EA over L. Okay? Nothing fancy. It's just a string element. Okay? So 29 e to the 6 times 50. 50 is a 50 cross section area. Remember, the length is 20 feet times 12. Okay, so you get this, the local matrix. Now, next step, you calculate the force from the thermal analysis, okay, which is negative E. What is alpha? It's provided 30 times E to the negative 6. Remember, watch out for the units. Okay, right here is always so nice, already in inches per inch. Okay, make sure they have the same common units before you work on it. And 20. 20 is the delta temperature. Okay, 20 Celsius. Okay, make sure the thermal coefficient is in inches per inches Celsius as well. Times area, which is 50. Okay, those two are the same. So you just calculate one time, and then you get two values, 8.7 times e to the 5. Now, you apply the boundary condition. I do not care how you name the nodes right here because I let you do it. Okay, but I named the node at the bottom as U1, U2, and U3. So right here, U1 is 0. Okay. The additions of two string elements, you should not have any problem by now. I hope not. Okay. This force is putting right here, but you add those two together, okay? Because the same thermal force is being applied to both elements. So this portion right here is all the thermal force, and then you apply the boundary conditions. F1 is some reaction force from the floor. Okay? F2, remember, is negative 1,000. Always remember, negative 1,000. And F3 is negative 500. The rest of it is very straightforward. You just multiply the, okay, always remember, double check, when we have a boundary condition on the right side, it's a known on the left. When I have a boundary condition on the left side, I have something to solve for on the right side. Okay? So you multiply that and you solve for U3 and U2 by row reduction. Okay? And you get U2 equal to 0.144 higher. Interesting. Look at that. The thermal growth is even stronger than the load applied to it. So instead of the whole thing being compressed and shorter, the thermal growth make the whole thing higher a bit. Okay, the total force, okay, max stress. From looking at the diagram, where will be the max stress? The elements at the bottom or the elements at the top? Obviously, it is the elements at the bottom because it's right here, the top elements is only experiencing 500 pounds of a force. But the one at the bottom is taking 1,500 pounds of force. Max stress is the force divided by area. So 1,500 pounds divided by 50 inches square, you got 30 psi. Now the yield strength for the steel is 36 to the E3. Wow, we only have 30 psi. Of course, this design is acceptable, and I would say it's kind of over-designed as well. Right here is kind of what you use for your midterm, your answers midterm. You just look for the yield strength for the material, your choice of materials. I don't care, aluminum, wood, steel, okay, and then you just compare the stress with the industrial standard. That's it. That's it for the
Hey,
whole
Chris,
final step. Yes, what's up?
I had a question about that exam.
Right.
So how do you combine the kind of the load in the X direction with the thermal load and then the axial load in the Y direction? Do you combine those elements or do you analyze them separately?
Hold on. You come to question 5.
Yes.
I have nothing on X. Everything's on Y.
No, I know, but if you did have a load in the X direction, kind of like the midterm exam,
Midterm exam for
the ANSYS midterm. So if I had a wind load in the X direction, right, and then I also
okay.
have a thermal load and a weight
I see
on
what
the
you mean
beam,
now. Okay, then
how do you analyze that question as a whole? Is
you
it
do
two
that
separate analysis, or is it
exactly. You do the same shape. Step 1, you analyze it as a beam, and then step 2, you analyze it as a rod element, and then you compare the stress. Which stress will kill you most?
okay? So I didn't understand if kind of the thermal expansion had any impact on kind of the wind direction when you're analyzing it from a using the beam element. If that makes sense.
Then you exactly, you in your assumption, you write that the geometry is the same. First step, I analyze it as a beam. So the wind is blowing on the side from it, try to bend that beam. And then after that is done, you redo the analysis, but this time same geometry, but you analyze it as a rod element or string element. And then you can input the thermal growth in it, and then you can do the axial loading on it. Because the result from both analysis is what? You get some stress. Then you calculate which stress will kill you most. Or even more conservative, you can add those stress together. Okay, from the wind bending the beam, I get what 500 psi. With the axial load, because you know what, the wind and the axial load is acting at the same time, right? So I get 500 psi from wind bending the beam, and I have another 600 psi from the axial load on the rod. Total 500 plus 600, I had 1100 psi from both load cases. And I use this value compared to ASME, ASTM, or metal supermarket standard, Wikipedia standard. I don't care. You pick one standard for me, and then I compare this max stress with the industrial standard. It's under the U string. That design is acceptable to me.
Okay, thank you.
Cool.
I just didn't know if they interacted with each other at all. Kind of the load coming from the X, and then the thermal stress,
So
and the actual load from the Y.
now I assume you are doing your answers midterm with hand calculation. Is that right?
Yeah.
Yeah, it's totally acceptable. Yeah.
Okay.
This is COVID-19 discount. Yeah. Happy?
Thank you.
You're welcome. Okay. So that's all I want to go through today. You have any questions for me? Anything like related to FDA answers? How you prepare for final exam? It's very similar. Well, you did your midterm very good. So I assume the same format will be applied to the final exam. I will let you have enough time to download the exam, you work on it, and you have enough time to upload it as well. And make sure you do not use very big pictures, okay? Because anything over 10 meg is a risk for you to upload it to Avenue to Learn. And guys, so any questions before we end this meeting? It's kind of sad. I only have 15 participants here. Okay? And seriously, I never uh, went through a past exam with students before. This is kind of my first time. And I hope you enjoy it.
I have 2 questions.
Yeah, go for it. I'm all yours. Yeah.
So the exam is next week, Saturday, 9?
From 9 to 12, yes.
Okay. And my next question is for the ANSYS term. Is it possible that we submit our midterms to you to kind of like proofread in a way, or just kind of like give us some pointers as to what to include, and then do like a final submission after? Would that be possible, or no?
Well, all the hints, all the tips, all the expectations I already provided to you already. Basically, you're saying that you want to submit a draft version, and then I give you some comments, and you submit back again.
Yeah.
Okay, unless you did very bad, I will give you some comment or feedback. Okay, it's way off, Mister. This is not way under my expectation, then I will give you some feedback. Yeah.
Okay.
But if it's okay, you know, and yeah, sorry, I think it's acceptable, and then I'll just take it. Yeah, that's right. Because it's 20% of the total score. If it is really bad, yes, I will give you some feedback. And but again, I'm not extending the deadline. Still, the deadline is still July 30th because I need to submit the final score to the faculty on time, and I need time to review your answers midterm as well. Okay. So before I end this meeting, any more questions? How many questions? Time and a half. Okay, how many questions will be on the exam? Around 4 to 5. Yeah, you will have two long ones, like just what I did before, and then probably three shorter ones. The thermal analysis is kind of short. Yeah. Question right here, question 2 and 3 is kind of long. Question 1 is kind of short as well. So two long questions, maybe 2 to 3 shorter questions. Anyways, okay, so that's it for today. If you have any more questions, send me an email. I will try to reply ASAP. Which should we focus on? All weeks. All weeks. Spring element, truss element, beam element, 2D elements, modal analysis, and thermal analysis. You might see a mix and match. You know, how to you must know how to join two different types of elements together. Okay. And everything's open book. You may, one thing for sure, you must have a healthy Excel spreadsheet to help you to do the 2D elements stiffness matrix, just like what you did on quiz 5. Okay, get it? You must have it. Okay. And other than that, that's all the tips I can share with you. Anyways, no stress. Okay, make sure you rest well and do not just memorize the examples or quizzes or previous exam. Understand each step. Why did I do this? You know, what's next? And then what? You know, that's the key message. Anyway, that's it for me. And thank you very much for joining this meeting. And I hope you have a very good weekend. Take care. Goodbye.